Okay, let's start this class. On Monday, we have briefly talk about what is pruning and what is sparsity for making the neural network, the transformers more speed up. And we have showing that it's like have a long history and many research has using those concepts, the pruning to making the neural network more efficient. And also in the industry, those like uh they have some hardwares can also support those kind of like a pool neural network, this sparsity in the neural networks. And we have like briefly talking about what's the key factors uh we should consider when we would like to deploying those pruning algorithms to neural network. We have I have mentioned the granularity and the pruning criteria, the like a pruning ratio, and also like if we need fine tune or not, or like fine tune or retrain the current neural network should be another factors. Like let's get into those factors one by one. First one is the granularity. Based on the name, we can guess, right? Neural network, they have lots of matrix. They have lots of convolutional neural network. We have those LSTM, those recurrent neural network. But in essence, the basic module in the neural network is the matrix, right? So um, we can prune the neural network at different granularity. Like here is a very simple example of those just one like a 2D weight matrix. Like if the most finest granularity will be like those weight level prune, right? We can mask some weights in this 2D weight matrix out, and we can get a very sparse like a weight matrix, right? And is the most fine-grained uh, pruning granularity, right? And we also call this kind of pruning strategy as unstructured pruning strategy because it is unstructured, right? Those prune weight patterns basically have no pattern, so it's like unstructured.
So are you pruning at random?
Not random, for choosing which element we should point out is based on the pruning criteria. We will talk about those criteria as a later, but I want to highlight this like a paradigm, those unstructured prune paradigm as an unstructured pruning paradigm. And compared with those pruning, like unstructured pruning, we also have those structured pruning. Structured pruning is more like it's coarse grained. It's not that fine grained. It's like this. Still using this 2D weight matrix as an example. It like if this is like eight times eight matrix, we can like prune some column out, right? And this is a structure pruning, like because if we can prune the weight matrix in this manner, we can get more compact like matrix, right? We can prune three columns out. We can get from this eight times eight matrix to like 5 times 8 matrix, right? And because this is it is more like this structure pruning is more easy to accelerate the whole pruning neural network, right? The reason is easy to understand because like we basically get a smaller like a smaller matrix, and this smaller matrix matrix multiplication is more faster, and the data's format is more organized. So even the I/O is more faster, right? On like the next thing, this is just a two more, just a demonstration about what is structured and what is unstructured pruning method. Uh, let's like this is like a for the convolutional neural network case, it's more complicated, right? Like because the example is just focused on the neural network on just one layers. The layer is a fully connected layer, but for the convolutional neural network, the convolutional layers is more complicated than just one just one like big like matrix, right? It has several is have the kernels architecture and how to like if we take a look at the case of convolutional layers, the pruning on those CNN are more complicated because we have those channel size, those output channels, those input channels, those kernels height and kernels width, so many dimensionality to be considered, right? So, like considering the pruning at CNN, because we have like more dimensionalities, so it gives us more choice to select the pruning granularity. For example, like the most extremely fine-grained pruning is like this format, right? We have several like kernels, right? This is basically a three times three kernels. We have six like in each layer, and if we do some like unstructured pruning or some fine-grained pruning, we can we can prune out some elements, and those elements have no patterns, have no uh, like basically have no patterns. So it's definitely we can do this kind of pruning. It can save like some like a weight size, like a model size, right? Because we prune out those weights, right? But definitely we can have some like a pattern-based pruning method, right? Because this is the most fine-grained, most unstructured pattern. We have different like levels of patterns. For example, we can like have those pattern-based pruning, like for each kernels, they have different patterns, but basically it's different from those most fine-grained pruning method. Those still have some like this pattern-based pruning have some like patterns, right? And we have those like vector level pruning is similar to the structure pruning in the previous demo. We can just prune out some uh, some column in the kernel thought, and then we can get a smaller size, but still very compact kernels. This is the vector level pruning method, and more coarse grain is like we can have those like a kernel level pruning, right? For example, like for this layer, originally we have six kernels, but if we can choose like those two kernels are like unimportant, we can just prune those kernels out, and most like we also have those channel levels pruning. We just prune some channels out, like in the convolutional network. So this is the process. This is the granularity differences. So definitely, as we always talking about the trade-off between efficiency and effectiveness, right? So, like, what's the pros and cons about those different the pruning, like a granularity? Let's to answer this kind of like a quick question or to analyze those kind of like trade-offs. Let's take a look at into some cases. So this is the most extreme case. This is a finest grained pruning method. Basically, we can like random like we can prune like the weight level. We can prune some weight out, right? It's the most extreme unstructured pruning method. But for those kind of like a fine-grained pruning method, the is flexible pruning indexes, right? Those uh like for any index of weight, we can prune it out, and because it's very fine grained, so usually we can like achieve larger compression ratio, right? Since we can flexibly find the redundant weight. But it's like because it's like very unstructured, so it's hard to get some like it's hard to get some general acceleration in like some in most of the devices, right? But definitely we can deliver the speed up on some like a custom devices, but it's not easily to get the acceleration on the most common devices like GPUs, right? And let's take a look at our second example on the pruning, the pattern-based pruning like a method. Basically, like this pattern-based pruning method, we can use this like a n versus m sparsity to accelerate those kind of neural network. Those n versus m sparsity means that in each contiguous m element, n of them is pruned, right? So as like for this kind of like a data, we can basically build a new data structure. This data structure is a sparse, is for those sparse weight, right? The most classical class is those uh, two versus four sparsity. So basically, in each in each data format, like this for this group, only two of them are empty. So it's like 50 percentage of sparsity. Like because if we use those like data format to represent this sparse data format is easy to compute, right? We can for this kind of data format, we can design the specific algorithms for their like a computation, right? They have some they have some algorithms for this kind of data format, but we will like skip the real acceleration algorithm in this part. Actually, this is supported by NVIDIA's AMP GPU architecture. AMP GPU architecture, the most famous devices is A100 GPUs. And uh, because NVIDIA have those like devices, they also have the CUDAs can support it can support this kind of like a sparse data format. So it can deliver up to two times speed up using this 50 percentage sparse data format. And it's like I think it's the most widely accepted, like a pattern-based pruning, like a kernels, right? The most important thing is that they, like NVIDIA, they realize those hardware and software. It's not just hardware and software. They have hardware, CUDA, like and software. It's a whole system, right? Hardware, the infra level, like it's the CUDA and the software level. They have those uh, uh, like a like a PyTorch to support the whole thing. So it can realize those like a pattern-based pruning acceleration. Uh, like so usually those are like a 50 percentage. Those two versus four sparsity can maintain the accuracy, right? It's like so it's like using this can break off those trade-off between efficiency and effectiveness. Like if we using the like a pruning algorithms properly, we can uh, guarantee no performance drop of those prune neural network, but enjoy those accelerations thing. And the third example I want to emphasize is the most like a cost grant annuity. Like basically we do those channel level pruning algorithms. We prune out half kernels, half number of kernels in the convolutional layers. The pros is like we can directly speed up due to reduce the channel numbers, right? Because like this is easy to understand, right? For example, like initially, like for this layer, we have six, for the original network, we have six kernels, and after using those channel level pruning method, we directly only have three kernels, and like the acceleration to saving the memory, saving the to saving the computation is immediately, right? So, but uh, the the drawback of those channel-wise pruning method is also very clear. The compression ratio is relatively smaller. Right? So uh it is like easy to understand this drawback, right? Because like intuitively, different layers should have different sensitivity to the pruning algorithms, right? Like it's not like a uniformly sensitive to the pruning algorithm. So definitely those like the channel level granularity should not be a good like a like a choice for the if we want to push forward to squeeze the performance of the pruning method, definitely those like a globally channel level pruning should not be a good choice, right? So the besides those channel level pruning, we have those like a layer adaptive channel-wise, channel level pruning algorithms. So like this AMC algorithms, like this ECCV 2018 paper, they propose this AMC algorithms is auto ML for model compression and acceleration on mobile devices. This paper proposed that we can do those non-uniform channel level pruning algorithms. It's like for maybe for the first layer, we just prune out like 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 half of those pair channels. But for the third layer, we can go further. We can prune out maybe 17% of the channels. But for the more sensitive, for other layers, more sensitive to the prune. So we can just prune 30%. Overall, the pruning ratio is like is comparative to the uniformed pruning, but the performance should be higher, right? Of those prune neural network. So basically, this is the granularity part of how we design the pruning algorithms. And the second factor is commonly be considered is the pruning criteria. We have talking about how to which part what's the pruning pattern we can use, right? This is a granularity, and the another thing in this pruning algorithm is the pruning criteria, right? We need to get the idea to for the algorithms which part and which weight should be pruned, right? So before we get into the algorithm's details, let's first think about for this very simple cases, like we have those just a one layer. It's not just one layer, we have just a one synopsis neural network like this, right? We have only three ways, W0, W1, W2. It's like this. And we only have just one activation function, which is a renew function. And here we get the y. For any input, x0, x1, x2, the output is y. So for this kind of simplest neural network, if we want to prune just one weight, which one we should prune? You can guess. Yeah.
The third weight, 0.1.
Oh, this one, right? The W2 one, right? So why?
Because the value is so small. Well, with it being less than 1, whatever x2 is will be scaled down significantly.
Yeah, that's a good heuristic for choosing those which are a weight we should prune out. And this is so-called a heuristic pruning criteria. Your answer is very correct. This is because this element, this base, the W2, contributed like less to the whole calculation, right? So like heuristically, intuitively, which can like if for those three elements, the most simplest one is this one. We should prune out this W2 one. So for those heuristic pruning criteria, we call it a magnitude-based pruning. Basically, those methods, those considers weights with larger absolute value are more important than other weights. Like basically for this, still for those simplest example is that we calculating which calculating the absolute value of W0 to W2 and we just rank those absolute values and find the if we only choose one, we just find the smallest one. If we choose two, we can choose like the smallest two. And this kind of method is so-called absolute, like magnitude-based pruning method. And it also can be used for the convolutional layers. Like, for example, for these 2 times 2 convolutional kernels, we can first calculating the L1 norm, like element wisely. L1 norm is basically the absolute value for different elements, right? And then we can get this matrix. And for this matrix, if we only want to prune, like if we only would like get a 50% sparsity for this matrix, we can prune out those two the smallest two like weighted, and then we get the prune weight like this. And like this is like the magnitude-based method for combining the unstructured pruning method, right? And how can we use those kind of methods for the structured pruning? For example, for the column-wise pruning, basically like we just generalize those importance concept into the column-wise. As here we like measure the weight importance, like element wisely, right? Using those L1 norm, those absolute values, but we can generalize those concepts into row-wise, right? And instead of just like we can calculating the L1 norm row-wisely, like taking like considering this as one vector, this as the second vector, and we can calculating each vectors like a L1 norm, and we can get this. The first rows like the L1 norm is 5, the second rows like the L1 norm is 6, and then we can. And because we hope to only get 15% of the sparsity, so we just prune the first column out, the first vector out, like we making those two vector, those two element as 0, and only like keeping the second row. This is how we use those magnitude-based pruning method for those structure pruning. And definitely we can like we can also modify those equation, right? Basically, like this is like we for those column-wise pruning, we can use this L1 norm to calculating the absolute value of the importance of the vectors. We can also use maybe L2 norm to measuring the importance of those vectors like this, right? And similarly, we can get even under those L2 norms criteria, we can find that this first row is not that important. So we pull out the first row, only keeping the second row. And our prune weight is like this. And also we can use like generalize those L2 norm into like some like LP norm, basically like many like lots of distance function can be used for measuring those importance, right? Okay, this is like the magnitude-based pruning method. Besides those magnitude-based method, we also have another paradigm for pruning is those scaling-based pruning method. Basically, it's a pruning criterion for filter pruning. It's basically specifically for the convolutional neural networks. The high level idea is to introduce a scaling factor, and this scaling factor is associated with each filter in the convolutional layers. And the scaling factor is multiplied to the output of these channels, and the scaling factor are like a train. Also, is the scaling factors are trainable parameters. For example, we like for different in this layer, we have those we have n filters. For each filter, we have a corresponding scaling factor like this. It's just a vector, right? And we can train like during the whole training process. We can also except we train those weight matrix like those filters. We can also train those scaling factors, right? And if like after the whole training, if the filters if the filter of output channels with smaller scaling factors, like those with smaller factors magnitude, we will prune out those kind of filters, right? Like this. If after the whole neural network with this channel scaling factor, after the whole training, if several factors corresponding scaling factor is smaller enough, like those two, we can prune those two channels out, right? Only keeping the filters with larger scaling factors like this, and then we can have a pruned neural network, and this is how we use those scaling factors idea for the convolutional neural network slimming. And actually this, yeah, go ahead.
So wait, could you train a network without the scaling factor and then just use like the L2 one, like the whole filter?
Yeah, you can use that. You can use that. But this is more like like the intuitive idea you mentioned is like more as before those methods, and after this method, this scaling factor thing become like a more mainstream solution for those filter like a channel wise pruning method. And yeah, and also these scaling factor things have inspired lots of like the concept of this scaling factor have inspired lots of like efficient AI works, like in our nowadays quantization, right? In the transformer, we like for comprising those large scale transformers, we also have those scaling factors to scale up to like maintaining the vector in the transformer in a proper range for easy to quantize. So it's an important concept in efficient AI, the scaling factor one. And this is the scaling-based pruning method. And basically the high level idea is not that hard. And the third paradigm is those second order based pruning method. This is like also very important. Actually, it's like the Lacan's work. I mentioned it's like 40 years ago work, but like the high level idea still works in nowadays large language model pruning, large language model like quantization. Okay, let's like dig into those methods. Basically, they calculating the derivative of the loss function in the neural network. They like the high level idea is minimize the error on loss function introduced by the pruning by pruning synapses, right? Because the objective of optimizing those neural network is to optimizing those objective function, those loss function, right? And also those pruning algorithms introduce some errors, right? Because like the pruning still like cause some errors for the loss function, right? So we can like calculating like what's the error in the caused by the pruning algorithms. Here is the here is the original loss function. We have the data. We have the W. Right? The W is the original weight in the unpruned network, and we put those like we also have the loss function for the pruned network, right? And this delta L is our is the error caused by the pruning algorithm, right? So for those like error, we can approximate by a Taylor series, right? The Taylor series is just some Taylor equation. We can like making the equation into different order of functions, right? And basically, like if we expand the whole function into the second order Taylor series, we can get this. This is the first order. This is the first order derivative of those loss of the loss function, right? Like this, and this is the second order term, like this, and this is the like a second order, but we can just ignore this part. It's too small, right? And for the this method, this optimal brain damage work, assume that the objective function is nearly quadratic, so this last term is negligible. It's very small. So they only keep the first order derivative and the second order derivative of those loss function lines. So we only need to focus on those these equations, right? And they also like have a like a assumption is that because the neural network training is converged, so the first order derivative of the whole loss function is also can also be neglected, right? Because for optimizing the neural network, we use the gradient descent algorithms to optimize the neural network, right? So as we can recall, the gradient descent algorithms for the using those gradient descent algorithms, we are calculating the first order gradient of the loss function for multiple times. Like eventually those terms can be like very small, right? This is the like a this is a hypothesis. But if this first order term can be neglected, so we can also get rid of this term, right? This is the first order in our Taylor series, right? And uh, And the third assumption in this work is that the error caused by deleting each parameter is independent. So basically, the cross term also can be neglected, like this term, because like a uh, like a deleting each parameter is independent, so this term can also be neglected. So the only for analyzing this like a pruning error, we only need to focus on this term, this second order. So we can get this equation like the pruning error can be approximated by this term. This HII is the the second derivative of each element in the neural network, right? And also this this is just element, but if we write those terminology in a matrix in a vectors format, this matrix in mathematical context is called Hessian matrix. But like so like using this equation, like this is the how can we calculating each element in the Hessian matrix like this using this equation, and basically the synapses with smaller induced like a pruning induced error, like this can be removed, and like so basically we can define the importance of each element using this Hessian matrix, right? So this is so-called like a second order based pruning method, and this Now this method, this second order analyzing, widely be used in how to comprise a neural network. I think nowadays even like the state of art LM quantization method, for example, like if you want to deploy those large language models, those open source large language models on using the Olama on your MacBook, you have some choice like int4, int8, like FP4, those choice, right? For most of like a low bit large language models, they are quantized by using those GPTQ algorithms. And those GPTQ algorithms also using this kind of like analyze method, those like Hessian matrix-based method to derivative their quantization method for the large language models. I think the GPTQ's paper, they also called optical brain damage. I forgot like the exact name, but they also use those GP like optimal pre-training brain damage thing, like those concept. Yeah. So when removing the neurons from the neural network models, the less useful, like basically the idea is like the less useful neurons should be removed, right? So, like if we can remove those less useful neurons, the better performance of the prone neural network will achieve, right? So basically, like we use those kind of like three paradigm. Like we have like nowadays we have like multi thousands of network pruning method, but basically all of them can be categorized into those three directions. At least most of them can be categorized. Mhm. And like this is the how can we choose the like pruning criteria? And our next question is how can we determine the pruning ratio, right? Like which pruning like a prune like how many sparsity we can get from the pruning network? And more specific is that how should we find those per layer like pruning ratio, right? And we also like in the second in the first like factory discuss how can we choose the pruning patterns. We have like mentioned that we can do those adaptive layer pruning ratio, right? But let's get into some details. So the question is how to, like the specific question is how should we find the ratio for each layer? So to answer these questions, we need to analyze the sensitivity of each layers, right? We need to like we need different pruning ratios for each layer, since different layers have different sensitivities to the pruning algorithms, right? So, we need to analyze which kind of layer are more sensitive. For example, is the first layer are more sensitive to pruning, or like and which layers are more redundant, which can be used to, which can be pruned out, right? So we can perform some sensitivity analysis to determine the per layer pruning ratio, right? So we do we do some analysis of those sensitivity of each layer. This is several years ago's work. So we use those VGG neural network on those CIFAR10 data set, and we pick the layer the layer Li in the model. For example, this is the zeroth layer, the first layer in the neural network, and the performance is like this. And if we prune the the layer Li with a pruning ratio from 0 to 90 percentage, we can get this curve, right? So basically, we can see that this higher pruning ratio, the more accuracy loss. This is very intuitive, right? And this should be the general trend for basically for every layers in the neural network, right? And this is how the first layer sensitive to the pruning ratio, right? Basically, if we prune only 10% of the parameters in the first layer, the performance still good. And if we can if we only prune like half of the parameters in the VGG net, it's still close to the original neural network, but if we put like 90%, it will lose lots of performance. And we do this kind of analysis to different layers. Like for example, the layer number 2, and we get these green lines. And similarly, we can do to the layer number 3, layer number 4, layer number 5, layer number 6. We can get 3 different lines, right? This shows 6 layers sensitivity to the pruning algorithms. So we can draw the conclusion is that some layers are less sensitive to pruning, like this kind of 3 layers are less sensitive to pruning, right? Even we prune out 90% of the parameters, it still have good performance, right? Compared with another 3 layers. Right, so we can definitely use this kind of characteristic of those neural networks. And some layers are more sensitive to pruning. So we can, the most intuitive idea is to set a threshold to choose the choose the sensitivity, right? We set the threshold here. Basically, we do not want to, we want to maintain the performance of the pruning network, at least this kind of performance. So we set this threshold here. And for different layers with different sensitivity, we choose different kind of pruning ratios. Like this. For these 3 layers, we can prune 90% of those elements. And for these 3 layers, we choose different pruning ratios. And for how to choose the parameter we want to prune out, we can we can use different criteria, right? Like we have talked about this. We have many methods to choose the to be pruned elements. And like after the whole algorithm, we can run those whole based on those uh, pruning ratio and pruning criteria, we can get those we can run those algorithms and get the pruned neural network, right?
Would you do this process like with your whole test set?
No, we do not have a test set. You mean the analysis, right? The analysis is on the test set. We can do it on the test set. We just want to like it's more specific. We do it on we can do it on the some validation set, right? We just want to uh, analyze to see if our hypothesis is true or not. Like our hypothesis is that different layers have different sensitivity, and we would like to take advantage of those phenomena, right? So like after we get these algorithms, we can do those automatic pruning algorithms, right? So we can find different like the optimal pruning ratios for different layers, and then we can get the like kind of like optimal pruning neural network. Right, this is like or this is a AMC method, auto ML for the model compression. And using this AMC, we can get very good performance. And those AMC algorithms, like at that time, have been used by many mobile devices, like on the Qualcomm chip and on the Samsung mobile devices. And this is how we like determine the pruning ratio. And the last factor, the last important factor is that should we how should we fine tune or retrain the pruned neural network, right? So basically, after pruning, if we do those pruning in a training-free manner, the model may decrease or like the model's performance may decrease, right? Especially for a larger pruning ratio. So fine-tuning the pruned neural network will help recover the efficiency, the accuracy, and push the pruning ratio higher. Uh, so the here is the basic pipeline of those deploying those pruning method. First, we train to get the connectivity, and then we prune the connections. And after we get the topology of the pruned neural network, we can train the weight again to recover the pruned neural network's performance. This is just an example. Basically, if we just run the pruning algorithms, like we can get the curve like this. But if we can also retrain like the weights in the pruned network, we can recover its performance back to like this, right? We can get a 80% prune ratio, and but maintaining the performance as good as the original unpruned network. And the most commonly used strategy is iterative pruning algorithms. Like iterative, The idea is easy to understand, right? Basically, we consider the pruning followed by a fine tuning as one iteration, and we repeat this iteration for several times. The iterative pruning gradually increase the target sparsity in the iteration. And for example, in the first round, we prune 30% of the weight, and we train the weight, and we repeat this pruning and training again. For the second time, maybe we can get a 50% prune neural network, and we retrain the neural network. And we can, for third iteration, we can get further, right? We can prune 70% of the weight out, and then we retrain the weight, and finally we can get good performance like the neural network, like the prune neural network with high pruning ratio, but the performance still very good, like this lines neural network, right? And definitely for the training process, we have in the machine learning course, you have learned some regularization tricks, the adjust those learning rates tricks, and many tricks for get a well-trained neural network, right? Those methods can be also used for training the prune neural network. Like we have those L2 regularization, L1 regularization, and many methods can be used in those in this fine-tuning process. So basically, this is our the topic I want to discuss about neural network pruning. On Monday, we briefly introduce what is pruning, what is sparsity, and in today's class, I have talking about the general pipeline about how can we get a good performed prune neural network. Like we have talking about how can we choose a granularity, what's the trade-off between different granularity, and we have talking about some criteria for the for choosing the pruning element, right? And then we have talked about how can we determine the pruning ratio, how can we using the analysis tools to get the optimal pruning ratios. And then we are talking about how to fine-tune the prune neural network to recover the prune neural network's performance. Okay, this is our class about pruning. For next class, I will talking about quantization. Okay, see you next week. And for maybe as this weekend, I will release our topic about our the final project. I will provide maybe 20, 30 papers you can choose as a topic. And okay, see you next week.
Number of fixed, how many persons will be in each group? How many students will be in each group?
I think 4. I haven't decided. Maybe 4.